Alrighty. So, today we're going to be looking at, we're going to start in section 6.1. So we finally hit the very first section of this chapter, right? We kind of jumped around. We started with 6.3, and then jumped to 6.2, and then jumped to 6.4, and now we're going back and finally hitting the very first section of this chapter in the book, slope fields and Euler's method. That's, you pronounce it Euler, not Euler. I know it's EU, you normally U, kind of like Europe, right? But it's Euler. From my understanding, that's how it's pronounced at least, okay? We're not going to get to Euler's method today. That'll be tomorrow. Today we're going to focus just on slope fields, okay? And looking at those and stuff, okay? So if you remember that a differential equation, right, involves one or two variables, okay, and a derivative. Solving a differential equation can be very difficult if separation of variables does not work, right? The only technique that we have to solve a differential equation right now is to separate variables, okay? But a way around solving a differential equation is to kind of use a graphical approach to analyze that solution to a differential equation, or at least using a graph to kind of help us at least try to understand what a solution to a differential equation might be, okay? And so this approach is to create a slope field, okay, like a field of slopes, which uses the derivative to find the slope at several points to paint a picture of various solutions, right? So this differential equation here, this differential equation, right, is the derivative of some function, all right? When we separate variables, we find that function, right? When we separate variables, so we have the dy's and y's on one side, the dx's and x's on the other side, and we integrate that, we find the solution of that differential equation, the original function, okay? That being said, there are some differential equations, right, of course, that we just won't be able to separate easily, so we can solve using that technique. So what can we do? Well, we can fall back on the idea that the differential equation here is the first derivative of something, so it describes the slope of that original function at different points, right, different values. Since this differential equation here that we've got, okay, is defined using both x values and y values, okay, both x and y values, different points in the coordinate plane will have different slopes, okay? So for example, all right, we'll just pick a particular point here. Let's just start at the origin. That's maybe the easiest here, okay? The coordinates at the origin are 0, 0, right? Oh, come on, Mario. So, for us to find our slope at the origin here, we're going to take our x-coordinate at the origin, which is 0, plug that in. So we'll evaluate dy dx at the point 0, 0. Okay? Which is then equivalent to just doing 0 times 0 minus 1. Okay? And what is 0 times 0 minus 1? What will that be? 0. Okay? What does a slope of 0 look like? It's horizontal, right? Horizontal. So at the origin, we're going to draw a miniature kind of slope there with a slope with a 0. Let's say it's horizontal, like a miniature horizontal slope there. Okay? So if our curve passes through, if our solution passes through the origin, at the origin, it needs to have a slope of 0. Okay? Okay. So what did we do here? We plug in the given x, y points to dy dx. Okay, to calculate the instantaneous slope at a point. Okay, that's what we're doing here. So you can see we have this grid of points, all right? And this is typical, right? Typically, you'll be given a grid, these big dots here to indicate find the slope at this point. All right, so all of these dots, we're going to find the slopes at those points, okay? That's a lot of little calculations, right? I mean, if you look here, what we have, like it's, what is that, 5 by 5? So there's 25 slopes there that we have to find, right? 25 little arithmetic calculations we'll have to do with our derivative. So a recommendation I have to you is to try to look for shortcuts. I'm going to put shortcuts in parentheses, or X quotation marks here, okay? Okay. For example, here, a good example is when like the derivative equals 0. Okay? We're pretty good at figuring out when our derivative is going to be 0 here. Looking at our differential equation, what x values will guarantee that our dy dx is going to be 0? When x is 0. Okay? So what y values will guarantee that our derivative is 0? Y equals 1. So let's just focus on the x equals 0 part first. On my y-axis, right, all these points on the y-axis, they're going to have an x-coordinate of 0. So at all those points, I can put these miniature slopes of 0 throughout. Okay, so again, we're just doing these miniature slopes. Okay, because it is really the slope at that instant. Okay, the slope at that instant we'd expect to be 0. Okay, just like that. Okay. Also at y equals 1. So y equals 1, that's this horizontal line, right? All these points have a y coordinate of 1, and so all these will have 0 as their slopes. So again, miniature slopes there, miniature slopes at those points, all at the slope of 0. Okay. So that still leaves us with 4, 8, 12, 16 slopes to find out. Okay? And all we're going to do is just, again, take turns kind of plugging in those slopes. So for example, let's try and find the derivative evaluated at 1, 2. All right, so 1, 2, we want to find the slope at this point. Okay, and so we're going to plug in 1 for our x-coordinate, 2 for our y-coordinate. 1 times 2 minus 1 is a slope of 1. Okay, so at this point, 1, 2, right, at the point 1, 2, the derivative of that is going to be 1. So the slope at this point should be a slope of positive 1. Okay, now, it's easy to graph a slope of 0, right? It's just a horizontal line. To graph a slope of 1, you can kind of use the points around it, right, to help you. So, right, a slope of positive 1 means you're going to go up 1, right 1. So our slope that we draw here should be kind of like in the direction of this point, right? Because that would guarantee a slope of positive 1 there. Okay. When you do these on the AP test, obviously this is not going to be a multiple choice question. This would be like a free response style question on the AP test, okay? The grader, won't be, necessarily looking to see that, oh, this says it's a slope of 3, but this looks closer to a slope of 4, okay? What they're more looking at is if their positive slopes are positive, if your negative slopes are negative, if your 0 slopes are 0, okay? Yes, you should still try to make them steeper if you have the slope of 4 versus a slope of 3, right? But don't, freak out too much, about, like, if they're going to take, like a protractor to it or something like that, so. Question?
X value -1.
For this point?
Yeah.
So for this point, the x-coordinate is just 1.
But the given point is -1, 0.
-1, 2. Oh, I see what you're saying. We're not doing this part just yet. We're still doing part A, sketching the slope field. We're still doing that. Yeah, we're still doing part A. We'll get to the sketching the different solutions in just a second here, okay? So it's important to understand what we're graphing right now. We are graphing the differential equation. The graph of a differential equation, or the graph of this differential equation, is the slope field. Okay, the graph of this differential equation is a slope field, or is the slope field right here. Okay. Okay, so continuing on. Right, continuing on here. So again, we'll evaluate the derivative now. Let's try it at, 2, 2. Okay. So 2 times 2 minus 1 2 minus 1 is 1, times 2 is 2. Okay, so at 2, 2, we need a slope of positive 2. There's no points over here for me to look at, but I can also go down to left 1, okay? And so again, I would, like a slope of 2, 2 would be something in that direction. Okay. And then so on and so forth, okay? We don't need to keep doing these, right? But for example, the derivative evaluated at 1, 3, okay? So 1, 3, so I plug 1 in for my x, that's going to be 1. 3 minus 1 is 2, so it's 2 times 1. Actually, maybe I'll write this one out. I'll do the first quadrant, and then we'll 3, 1, 1, 3, Mr. Wid, 1, 3. Okay, so 1 times 3 minus 1, which is going to be 2 as well. So the slope here at 1, 3 is a slope of 2. Okay, and then I'll do one more on the paper here. We'll do 2, 3 to finish out that first quadrant there. Okay, so then 3, let's see, 2, 3 minus 1 is 2, so 2 times 2 is 4. So now we have a slope of 4. And let's see here, slope of 4, we go down 1, 2, 3, 4, left 1 there, so it's going to be something like aiming towards that point there. Okay. So there's kind of my first quadrant, right? But goodness, we still have a bunch of other points to do here. So if you'll permit me, we'll just kind of go through these a little bit at a time. Any questions so far, I guess, on just these points? Okay, it's just a bunch of arithmetic we got to do here. All right, so let's just go through here. All right, here we have the coordinate 1, 0. So it'll be 1 times 0 minus 1, so 1 times negative 1, which is negative 1 slope. Okay, 2, 0, so 2 times 0 minus 1, so it's going to be negative 2 slope. Okay, there. Just going to have that slope of negative 1, slope of negative 2. We'll do 1, negative 1. Okay, so 1 times negative 1 minus 1, so negative 2 will be that slope. And then 2, negative 1. 2 times negative 1 minus 1, so it'll be negative 2 times the 2, so negative 4 slope there. So it's a little bit steeper. Okay. Now, of course, as we're filling in this slope field here, it's important to understand, right, that we're finding the slopes at these particular points, okay? And they're nice points, right? It's just whole number points or integer points, right? But we could, if we wanted to, we could find the slope at like 1/2, 1/2, right? We could find a slope here too, all right? That might be helpful to, kind of give us more details, right? The more points, the more slopes of points at points that you find, the more kind of detail you can see about the behavior of a particular solution or something like that, okay? But it also just gets a little tedious having to do all those slopes, and it also gets a little messy having all those slopes graphed, kind of in a very concentrated area. So it's kind of like a balance that you want to give to yourself, where it's like, how many points do I want to graph to get enough data, but also I don't want to graph too much that it's just like a sloppy mess. Well, we're all awake now, right? All right, so anyway, don't worry, I'll put you back to sleep with some calculus. All right, so here we go. So negative 1, 0. All right, negative 1, 0 minus 1. So it's going to be negative 1 times negative 1, positive 1. Okay, negative 1, negative 1. So negative 1 times negative 1 minus 1. So it'll be positive 2 will be that slope. All right, let's do negative 2, negative 1. So let's see here. Negative 2 times negative 1 minus 1, so it'll be positive 4. Okay, and then negative 2, 0, negative 2, 0 minus 1, so positive 2. Okay, and then we'll finish off these points right here. Typically, these slope fields, by the way, on a free response question, they're worth 1 or 2 points. Okay, so if it's worth 1 point, that means that if you miss one slope, you don't get the point. All right, so you want to be very careful with these. All right, if it's worth 2 points, typically that means that you'll get like 1 point for like all of like the positive and negative slopes, and then maybe 1 point for all the 0 slopes, something like that. So again, my point is here that with all these little calculations, be very careful, because if you just miss one, you'll lose that point. Okay, so please be very careful with all these little calculations and stuff. Just be careful. So negative 2, 2. So let's see here. Negative 2, 2 minus 1 is 1, so it'll be a negative 2 slope. Negative 1, 2, so negative 1. 2 minus 1 is 1, so negative 1 slope. All right, negative 2, 3, so 3 minus 1 is 2, so negative 4 slope. All right, and then negative 1, 3, negative 1, 3 minus 1 is 2, so negative 2 slope. Okay, and voila, there it all is kind of filled in. Okay, now remember, these are slopes of our curve, right? It's a slope field. It's a field of slopes, right? Depending on the location of where we start our curve is going to then determine kind of the direction that our curve follows. And this field of slopes helps to kind of like guide you. Okay, if you look at it there, you can kind of see, you need kind of like picture what a curve might look like in this, scenario. Okay. So let's move on here to letter B, all right, and sketch two different graphs given that the solution passes through 0, 0, and negative 1, 2. So we're going to be graphing graphs here of solutions to the differential equation. These graphs that we graph are going to be like the original functions. Okay? And they're going to be particular solutions. One particular solution that has the point 0, 0. So this is imagine, if you think about it, right? This is like taking that differential equation, solving the differential equation by separating variables, and then plugging in that 0, 0 to get your C value, right? So that would be for that particular solution. And then alternatively, solving that differential equation by plugging in the negative 1, 2, and then finding that C value. So these two different C values are going to result in different graphs. All right, I'm going to try and do these in different colors here. Let's see, do I have... Let me see if I've got a blue one over here. Do a highlighter. Work. Nope, I've got a blue one here. All right. So I got green and blue. I don't know how well they're going to show up, but we'll give them a try. All right, so let's do the 0, 0 one. We'll do that one in green, which looks pretty dark to me, but there. Okay, we'll see. Maybe if I turn on the light, does that make any difference? Maybe not. Okay, so 0, 0, we're going to start right here. Okay, and our curve here, right, has a horizontal tangent. And then as we go to the right, how should we proceed? What does the behavior, what behavior should we kind of show here or portray as we go to the right? What should happen to our function? It should decrease, right? It should curve downward. As we go to the left, what should happen? Curve downward as well, because these slopes are indicating that. And so in fact, that is what we're going to do. Okay? Now, you do not need to go through a point. Okay? You do not need to go through and hit like a particular point here. That's not the goal. The goal is to kind of just use the slope fields to help you graph the solution here. They just kind of guide you. Okay? They just kind of guide you. So the fact that I went through the point, negative 1, or 1, negative 1, not necessary. Okay? In fact, you don't need to, but it just kind of happened that way as I was kind of showing the behavior. All right? We'll do the same thing then for negative 1, 2. We'll do that in blue. Again, I don't think that really shows up that well, but anyway, I tried. All right? So negative 1, 2, now we'll locate that point. Here's negative 1, 2 right here. Okay? So we know this point will be on our curve. All right? Just like we knew 0, 0, that was going to be on our curve there. So negative 1, 2 is definitely on our curve. I can make a big old point there. Okay? And then as we go to the right, what kind of behavior should we be exhibiting? The slope here is negative, right? It's a decreasing slope, and so we should be going down, right? So we're going to go down. But should I decrease forever? No, because what should I do at y, the y-axis here? It should be like a minimum, right? It should bottom out because we have a slope of 0. Okay? Now look, I'm not hitting 1. I don't need to hit 1, okay? I just need to show that I'm decreasing and then gradually going to a slope of 0. And then beyond this, what should I start to do now? Increase. Okay? And then increase more and more steeply, right, as we go. What should I do as we go to the left? I'll get you something in 1 second. What should I do here as we go to the left now? start to increase, right? Or go up to the left. Okay, and voila, there is our other curve. So, send me a question.
Did you also make it a curve that like starts, I mean, always decreasing? So you start from the side and then you equal out at 1 and then you go downward?
So you're saying like would it approach like this as like a horizontal asymptote? You're saying?
And then just go downward.
So good question. All right, let's imagine here though. So let's say we did that, right? So first of all, we're starting above 1 here, right? And so if so you're saying kind of beyond the y-axis, right? Can it kind of like approach and then start going down, right? That's your question. All right. So looking at our x values here, we're either going to be in quadrant 1 or quadrant 4. Our x values will always be positive, right? Our y values here, okay, our y values, well, we're starting above 1. And so the question is then, Simeon, do our y values get to be below 1 or do they always stay above 1? And well, the answer is we don't necessarily know. We don't necessarily know, right? But, you know, if you kind of, and that's again where we could use more slopes if we wanted to kind of convince ourselves. So for example, we could find the slope here, you know, in this, like we could find a slope in this kind of general area, maybe like -1.5, 1.5, and see that the slope is maybe not as steep as this slope, so it's like, okay, maybe we are bottoming out, and so that would indicate that. If, however, the slope was like even sharper, potentially then we would cross through, and then we would want to follow those behaviors. But with the general kind of thing here, it looks like our slopes are, you know, less steep as we move in towards y, and then they start to get, you know, more steep as we move further away from y. So it looks like that's the kind of idea. So yeah.
So why does it not bottom out to 1? Or does it?
So why doesn't it just go flat down to the 1 there?
Yeah, why doesn't it just even touch the 1?
Well, so once we move beyond that y-axis, our x values are certainly positive, and so this part of our differential equation, will be positive. Okay? The y values then, those can go positive or negative. Well, since it seems like we're going to be staying above 1, the y values will be positive as well, so a positive times a positive would indicate positive slopes, which means we should start to increase again after that 0.
Yeah, but how come it doesn't reach the 1?
How come it doesn't reach the 1? Well, again, we don't know for sure that it doesn't reach the 1. We're kind of giving our best estimate there. And again, just with kind of like the way that the behavior seems to be, it looks like it doesn't quite reach that 1 there, yeah. And again, if you look here, the slopes are kind of indicating pulling away from that as well, okay? It'll be different if like all this, so let me show you this. It'll be different if our graph of our slope fields looked something like this. You know, where now it's like, okay, it looks like it's going to come in towards kind of thing. But these are all seemingly pulling away, you know, kind of thing from that. Okay. So. All right. Questions on any of that? All right. So we're not quite done yet, right? We have part C here still. And by the way, this is like a very, very typical format for a free response style question that, you know, you'll see on like the AP test or something like that. Very typical kind of format where you'll be given like, do this slope field, sketch some particular solutions, and now come up with the actual solution to this differential equation by separating variables and stuff like that. This is like a classic kind of question that you'll see on the AP test when you take it in May. Okay, so letter C, now let's actually see if we can find the solution to the differential equation dy dx that is sketched through. Now we're going to use only 0, 0, right? We had 2 different solutions here we were considering. Now we'll find the actual 0, 0, 1. Okay, so dy dx equals x times y minus 1. And how do we solve a differential equation? What do we do? Separate the variables, right? Dx and x on one side, dy and y on the other side. So we're going to get 1 over y minus 1 dy equals x dx. And then we're going to integrate. Please make sure you draw on those integral symbols. Okay, very important to have those there to kind of show what you're doing. Okay. When we integrate 1 over y minus 1, technically we should use what technique? We're going to use natural log, but I mean, technically we should use a u substitution here, okay, technically. Now, is it necessary for this particular situation, this instance? No, because if we let u equal y minus 1, du will just be dy, and we're fine there, okay? So you don't need to use a u substitution for this, but understand that when you do have more than just y in your denominator there, you know, if you have like y, you know, well, I guess if you have, I want to be careful, like 2y minus 1 or something like that, you do want to use a u substitution. But here, you can get away with it, okay? So if this were like 2y minus 1, you definitely want to use a u substitution. But for now, we don't need it, okay? So I'll go ahead and just, you know, do it. Okay. And again, you can check yourself to make sure. If I take the derivative of the natural log of the absolute value of y minus 1, the derivative of that will be 1 over y minus 1, right? That is what we get. So I know that we took the integral correctly there. Same thing here. If I take the derivative of this, the derivative of 1/2 x squared is just x, and the plus c is a constant, so it goes away. Okay? We're not done yet. We still got to figure out what the solution is at 0, 0. Okay? So I'll go ahead and, for this one, I think I'm going to solve for the y first, and then we'll plug in 0, 0. Okay? So I'll e both sides, so we'll have absolute value of y minus 1 equals e to the 1/2 x squared plus c, like that. That plus c in the exponent, what can we do with that, though? We can pull out front, right? Because, again, the idea here is this is e to the 1/2 x squared times e to the c. E to the c will also just be a constant, so we end up with c e to the 1/2 x squared, absolute value of y minus 1. Okay, which you can then rewrite as y minus 1 equals plus or minus c e to the 1/2 x squared. Okay, which then gives us y equals, I'll go up here, y equals 1 plus or minus c e to the 1/2 x squared. All right, and we got to find our c value, right? So we're going to plug in 0. Okay, we're going to plug in 0 here. So we get 0 equals 1. And I'll do the 1 plus version here. Oops. And I'll do the 1 minus version here. Okay. If we solve the c value here with 1 plus, well, let's see here. 0 squared is 0 times 1/2 is 0. E to the 0 is 1. So I get 0 equals 1 plus c. So c equals negative 1. Whereas here, 0 squared is 0 times 1/2 is 0. E to the 0 is 1. I get 0 equals 1 minus c. So c is positive 1. Okay. When I go to check these back in, remember that I got this particular c value from doing the plus, right? I had plus or minus c. I got this c value from doing plus c. So this one's y equals 1 plus negative 1 e to the 1/2 x squared. Whereas this one, I got the c value from doing the minus c. So get y equals 1 minus 1 e to the 1/2 x squared. And what is true about both of these curves? They're the same, right? So we don't need the plus or minus. We can kind of like forget about it here. And I'll just use this version right there. Okay. So we'll just use that version right there. Okay. And so there is our particular solution there. Okay. Questions on any of that? Oops. Right. This calculator is annoying. So. Okay, and so sure enough, if you look at the graph, whoops, I'm frozen. If you look at the graph of our solution curve there, it is kind of like parabolic looking in nature, and there is our kind of estimated graph right there. So not too shabby, right? Not too shabby. All right, let's move on here. All right, number 2. Another slope field. Okay. So again, this creates a slope field. Okay, that differential equation is what creates the slope field. Okay, so we're going to create this slope field here, construct a slope field for these 16. Oh, they were very kind to us here. 16 ordered pairs shown below. Yeah, 16. Okay, this one is not as friendly because we don't have an easy way to get 0 here for our slopes. Okay, except at the origin. The origin 0, 0 will give us a 0 slope, so I can go ahead and graph that horizontal line in. Okay. Also at 2, 1, 2 for our x coordinate minus 2 times 1 for a y coordinate there, so that will also be a slope of 0. Okay. But sadly, those are the only 0 slopes. So all these other ones we have to just kind of do some calculations here. So again, I'm just going to run through these here. It's just a bunch of arithmetic, right? So I'll start with the x-axis here, the point 1, 0. So 1 minus 2 times 0 is just going to be a slope of 1. Okay, and then 2 minus 2 times 0, so a slope of 2. And you really have to eyeball it here somewhat because you just don't have other points around you to kind of help figure it out. So I just use those to help you there. Okay, negative 1 on the x-axis there, negative 1, 0, is going to be a slope of negative 1. And then negative 2, slope of negative 2. So just draw like a little bit steeper. All right. Now we'll go across the y-axis here. And I recommend, this might be a better way to do it here, is to kind of like try and stick either going all across, so do like all the horizontal ones, so that way you can at least keep your y values, for this case, the y values will always be 1. So no matter your x value, you're always going to be just subtracting 2, right? Because y value is 1, so minus 2. So for example, negative 2 minus 2 is going to be a slope of negative 4, so super steep. Right. Negative 1 minus 2 is negative 3, so a little bit less steep, but still. And then 0 minus 2, so a slope of negative 2. And then 1 minus 2, so a slope of negative 1. Like that. Okay. And then this top row, again, always the y value is going to be 2, so I'm always going to be subtracting 4 here. So negative 2 minus 4, negative 6, really steep. Okay. Negative 1 minus 4, negative 5, so again, steep again, just a steep negative slope. 0 minus 4, negative 4, so again, just steep. 1 minus 4, negative 3. And then 2 minus 4, negative 2, so a little bit less steep there. And then the final one at 0, 3, so 0 minus 6, so a negative 6 slope, again, very steep. Okay. So this one maybe not so obvious about how our curve is going to be, right? You can kind of get an idea. All right. Something that is kind of like maybe good to analyze here, though. dy dx equals 0 when 0 equals x minus 2y. Or in other words, 2y equals x, or in other words, y equals 1/2 x. So any point along the line y equals 1/2 x is going to have a derivative or a slope of 0, okay? So if you can imagine here, right, if I were to draw in the line y equals 1/2 x, in fact, I might do that here just kind of like very lightly. Starting at 0, 0, right, because that doesn't have a y-intercept, so it's a slope of 0, or not slope, y-intercept of 0, and going up 1, right 2, up 1, right 2, there's another slope of 0, right? If I went down 1 and then left 2, I would expect a slope of 0 here as well, and any point, I'm going to draw this very lightly, any point along this line here is going to have a slope of 0, okay? Any point along this line is going to have a slope of 0. Okay, because it follows this rule, And so you're going to end up with 0, right? This will be helpful when we go to sketch our solution curve next. Okay, so our solution curve, we want to go through the point 0, 1. So I'll do mine in green here. Okay, to sketch our solution curve, 0, 1. So 0, 1, this is our first point. So make a nice big dot there. And according to the slope at the point 0, 1, what behavior should we do to the right of this point? We should be decreasing. But then this line right here, what do we know? All the slopes along this line have to be what? 0. So where we cross this kind of like line, we should what should happen to our graph? It should kind of like bottom out, yeah. Okay. So I'll do that, and then what do we think should happen now that we've kind of gone through that bottoming out? Oh, I didn't bottom out very well there. What should we do now that we've kind of bottomed out there? What should we start doing now? It looks like we should start increasing. Okay, maybe very gradually here. Something like that. Okay. And I'm not really sure beyond that. How about to the left of this point right here? Increasing, yeah. And just increasingly increasing, right? Okay. At this point, I'm not sure if we should maybe cross this again. That would indicate kind of like a bottoming out, but I'm not sure. I'm not sure what to do from the right there. Okay. So we'll just kind of like stop it right there at least. Maybe we know we got to go through there. Maybe I should have gone more flat like that. I don't know. Say what now? Also kind of flat. Well, so if we're under the 2, 1, we won't quite be flattening out. It's at the 2, 1 that it would flatten, or any point along this line. So we're not here. It's not like a vertical. All these slopes won't be 0. It's only slopes along this line. So whenever we cross this line, it should bottom out or kind of like top off, but not right there. So this is a bit harder to see. And it's going to be even harder to see because, well, can you find the solution to this differential equation? dy over dx equals x minus 2y. No, I mean we could add 2y over to this side, okay? So if I do that, we'll get 2y. But if I'm adding 2y to both sides, it's 2y plus dy over dx equals x. Right? And then I can multiply both sides by dx if I wanted to. But if I multiply both sides by dx, I will end up with x dx over here, so that's good. But if I multiply this side by dx, what am I going to end up with? 2y dx plus dy. Okay, you can see here that there's not really a way to separate the variables, okay? So, no, cannot separate the variables. Okay, so we actually can't solve this differential equation by hand, okay, with our current techniques that we have. All right? Question on any of that? So that one's a little bit disappointing because you can't solve it. So you really can't check your curve to see if it looks right or not, kind of thing. Okay? All right, let's move on here to number 3. And why don't you guys go ahead and take a shot at this. All right, so A, B, and C, okay, these are your differential equations. So you've got 3 slope fields here, okay? And so match these 3 differential equations, A, B, and C, these are the differential equations, to their slope fields that they would produce. And then, if you're feeling, like you got it or you want to give it a try, then D, E, and F match the solutions. Okay, match their solutions. So which one of these 3 slope fields will produce a curve that looks like y equals x squared? Which one of these 3 slope fields will produce a curve that looks like y equals e to the x? And which one of these 3 slope fields will produce a curve that looks like y equals e to the x minus 1? So go ahead and take a look at that. Try and figure it out, All right, and we'll see how it goes here. Yes. How is he, Mario?
When I picked him up, he was, he didn't look too good.
Okay.
When I talked him up in the hospital, the doctor said he would be okay, that
Okay.
it's just bruises in his blood.
Yeah, goodness.
So apparently he was driving on a bus center, and
Okay.
he hit a deer,
Oh.
and so then the deer made his truck go out of control and then he hit a tree. And so the truck's like totally totaled.
Yeah. That's deer, man. I tell you what. Crazy. Okay. So, this first slope field, A, B, or C? Which one does it match? B. Okay, so let's take a look here. What is unique about the differential equation for B that's not true for A and C? The differential equation is defined only by what variable? X. This one is defined by X and Y. This one is defined by just Y. So the differential equation here is only defined by X. So in other words, the slopes will only depend on the X value. Okay? The slopes will only depend on the location or your X coordinate kind of thing. So if you look here, right? Okay, the X value of 2, no matter the Y value, all those slopes are what? They're all positive. They're all going to be the same slope, right? If you look here at the X value of 1, okay, the X value of 1, no matter the Y value, all those slopes are the same. So these slopes are only dependent on what the X value is, not the Y value. These other ones here are different than that. So yeah, this is B. Okay, that is B. Okay. Other strategies you can use here. Well, I notice what kind of slopes do we have here at the y-axis? The slopes are all 0, okay, which means at an x coordinate of 0, no matter the y coordinate, the slopes are 0. Here, if I have an x coordinate 0, the slopes would still depend on what my y coordinate is. It would change. Here, if my x coordinate is 0, my slopes will be 0 no matter what. Here, if my x coordinate is 0, well, it doesn't depend on my x-coordinate at all. It just depends on the y-coordinate. And again, the y-coordinate is changing here, but the slopes don't change, right? So it wouldn't be C. It's going to be B, okay? So one point or one kind of like clue or help, tip I give you here is look for 0 slopes and see which differential equation would result in 0 slopes at those particular locations, okay? Or seemingly 0 slopes and stuff like that. All right, how about this one right here? Or actually, maybe we should jump to this one first. I think this is a little bit easier. What will this one's differential equation be? It's going to be c. Okay, right. Okay, because here, no matter the x-coordinate, right, as you go left or right, all those slopes are the same as you move left or right. But it's what does depend. It's the y-coordinate, whether you're moving up or down there. That changes your slope. Okay, and so it's not dependent on x and y. It's just dependent on the y. So it is c there, and that leaves this one to be what? A. Okay, which makes sense because depending on where you are, the slopes change, right? So, and you can kind of like, again, eyeball it here. So like at 1, 1 plus 1 is 2. Yeah, it's a positive slope, 2, stuff like that. Okay, pick particular points and check those and stuff like that way too. Okay, so there's the idea. Questions on any of that? Okay, I see a 0 slope here at 1, -1. 1 plus -1 would give me a 0 slope. Okay, so that's the idea. All right, moving on here. What solution? Okay, so which one of these, is it D, E, or F for this guy right here? D, right? That looks like a parabola, right? It looks like a parabola. Okay, it looks like a parabola there. All right, and then of course, so which kind of makes sense, right? Because if we were to solve this differential equation here, if we were to integrate this, we'd end up with x squared plus c, right? X squared plus c. And that plus c is going to shift that parabola up or down, which is what you can kind of see here. You can see a bunch of different parabolas that we could draw, and the only difference is they're shifted up or down from one another, which is what that plus c would affect, right? Okay, how about, again, we'll skip this one, we'll jump to this one. How about this one here? What would this one's solution curve be? No clue. Oh. Lander says he has no clue. I don't know if you speak for everyone. So it is going to be, so the curve of, the graph of y equals e to the x. What is the graph of y equals e to the x look like? Like that.
Like that. That's what I was doing.
Yeah, no, I understood. Yeah. When you said that, you mean that.
Yeah.
Okay, it's exponential, right? Okay. So which one of these curves is going to match that behavior? It's going to be the third one here. Okay, so this is E, which leaves this one here to be F. Okay, which leaves that one there to be F. Okay, remember that this is just one possible solution. So the e to the x, it would be like this, right? But of course, if you had a negative c value, then that would create the curve that would go down this way, okay, for negative c values there. Stuff like that. Okay, questions on any of this? All right. So why don't you guys go ahead, try this one here on your own, okay? So this next one here, oh, trig, okay, trig. All right, so give it a try. See what you come up with here. All right, give that one a try. This will be our last problem we'll do here together. Right, we'll be done after this one. Okay. So construct your slope field. Sketch the graph of the solution that passes through the point -1, 1. Write the equation of the tangent line to y equals f of x at the point 1, 1/2, 2. And then letter D, determine whether the graph is concave up or concave down at -1, 1. Okay, so notice you're not finding the particular solution here. Okay, you're not finding a particular solution here. Okay, so give it a try. Okay. Question? Say again?
Is B a trick question? D? How did you determine it was 0? But remember to determine the cavity, you have to look at what derivative. Second.
Yeah, say that out loud.
So understand,
the slope here, okay, the slope here is the dy dx. What you graph right here is a particular slope. So what you graph here is like the is a graph of the original function, not the derivative, right?
But the derivative at that point is zero because it's flat.
I'm actually trying to get better.
The derivative of the original function is 0. So here again, what I would suggest you do. I mean, so you're like, I don't want to say too much. I want you to be right for the right reasons here. So actually take the second derivative,
Yeah.
plug in your point, and then use that for your analysis. Okay. Okay. What is that? What you're asking? When are we gonna play Heads Up 7 Up? She doesn't.
No. Construction zone included. That would be cool. But we wouldn't be able to walk. We'd have to get like a gator to be able to search. Let the medics ride on. You work with medics?
What? No, it's
We're not. Let's focus on what's important. How do you think who's going to see first?
I'm right there. 1 sec. We're in real life right now.
Not think outside of the classroom and not including my department.
You probably won't. What were you planning on doing after?
It changes every week. I'm a dentist. I was a psychologist.
So yeah, probably not either.
I was a damn psychologist.
Probably
Not really the best idea.
Physical trainer or vector field.
That was like second grade. I was a meteorologist. I did a weather phase. I watched it really.
You know, it's like you're predicting the
You're
future.
getting paid and you're wrong a lot. Well,
How do you know? What is that the slope of though? That is dy dx first. Cavity. Second. Okay. So your answer's going to turn out to be right, but not for the right reason. But it's not increasing. The function is not increasing or decreasing. When you graph a slope field, you're graphing solutions to the first derivative. The first derivative is 0. At that point, yes. That means the function is not increasing or decreasing. You want to know if the function's a slope of 0 though doesn't necessarily mean that you're not concave up throughout the whole scenario. For example, like a quadratic, right? So you'll need to actually find the second derivative. Plug your point in.
If you think about it logically, yeah, that's what I had originally.
Can you just use your graph?
Part of it was I just recognized
Kind of, but again, your graph is imperfect, right? If you make a mistake, find the second derivative, Lander. Find the second derivative. You have the differential equation. Find the derivative of that. Proceed. Okay. You give up?
Yeah.
Don't give up, Lander. Just take the second derivative. It's not that bad.
On my answer.
Okay. So hopefully your slope field looks something like that. Something like that. Okay. The solution to this differential equation is or the graph of it, I should say. Okay. Something like that?
I did not get that.
Yeah, that's why. Yeah, that's.
Okay. There's your equation for your tangent line.
I got it.
Got it. Okay. And then when we go to take the derivative of this, because to determine concavity of a function, we need to look at the second derivative, right? What is the derivative of y with respect to x? dy dx. What is the derivative of cosine with respect to x? Negative sine pi x times the derivative of what's inside pi. Okay? What is dy dx? It's up top, right? Y plus cosine pi x. Okay? We plug in the point negative 1, 1, because that's where we want to determine the concavity, right? We're looking to see if our second derivative is going to be positive or negative for concave up, concave down, okay, respectively. Plug in negative 1, 1. Okay, like so. What is cosine of negative pi? 1 plus negative 1 minus. Let's see, what is the sine of negative pi? 0 times pi, still 0. So 1 minus 1 is 0, minus 0 is 0. So, is the graph concave up or concave down? Neither!
There's no third option. It has to be one.
It's kind of frustrating, right? Not very satisfying. Okay. Yeah, it should put like if neither, then say so too. Like you're saying it's kind of like it does Sarah, were you saying it doesn't give you like a hint of the fact that it's like up, or that could be neither? It is kind of tricky. I get you. All right, so that's all I've got for you guys today. You can get to work on the problem set. I'll also post the homework to Google Classroom here, so you can get to work on that. Okay.
Just so when my
Yes, I'll get that to you. Let me just get this
I
posted.
have a question on my book.
Okay.
did a lot wrong. Yeah, usually I don't do as good as the average. So I go against my Southern Garrett kid, right? We have two matches this week. One against Southern Garrett, which is like 2 hours away. And then we have Century, which is like over by Westminster. And so I go against my Southern Garrett kid and I win. The Century kid as well. So
Yes.
Yes,
Yes, he was. Yes. Pretty cool, huh?
Pretty cool. I guess he didn't want to run.
But it was actually, when he was there, it was warmer there than it was here. If there's summer there,
Yeah, I'm a one.
and he's also on like one of the northernmost tips of the Antarctic. If you like, if you look at a map of the Antarctic, it has this like kind of like peninsula, I guess. It kind of juts out pretty far from like the south, from the centrally kind of south part around the South Pole, you know. So and that's where they.
It's really cool.
I think. Right. Because I think at some point when we were having that cold weather, it was warmer here. Or sorry, it was warmer in Alaska than it was here. Like they were experiencing like a heat wave, and we were experiencing the opposite.